Hi, I'm Guiche, and I'm going to tell you a story today about JIT compilers. But so first, things first. So I will put again this slide. I am Guiche. I added in this slide now this first line that says how to pronounce my name. It's in the International Phonetics Alphabet. So if you know it. But getting a version that is kind of writable in English is kind of complicated. I will put the Japanese version because it's easy to write Guiche in Japanese. So I'm going to talk about JIT compilers a bit, or not. So it's more about debugging JIT compilers and debugging assembly code. We do this a lot, so we have tools to help us debug our JIT compiler. So here, for example, we have this is a machine code debugger that we use to debug. We can use it to debug Intel 32, x64, ARM64. But this talk, so I don't want to bother you with details that you don't care about. So we want to debug the assembly code without looking at the assembly code, right? So yeah, how do I do that? So for that, I need to give you before this talk, so before not going into the assembly code, I'm going to give you a quick overview on the context. So why I'm debugging this JIT compiler. So the Faro VM, grosso modo, has several components. One of the ones that are interesting for us today, we have an interpreter. It's not readable, so I will change that before giving people the slides. We have JIT compiler, we have FFI concurrency, we have a garbage collector. So pretty standard. And now we have a new project that is coming to life that is called Druid. That has as objective to generate the front end of the JIT compiler based on the interpreter automatically. So the goal of this is that if I change the interpreter, so any of you can change the interpreter, it's easier to change than the compiler. And then you get a JIT compiler for free. Yes? So the idea is to shift a bit the maintenance of the JIT compiler between the different people. So people that care about the semantics of the language, they change the interpreter. People that work on optimization, they will work on this meta compiler that generates the JIT compiler, or they will work on the backend of the JIT compiler. So, of course, this project is not mine, so it's mostly Nawel's project right now. So that's Nawel, the Rasta guy. So he's working a lot on this, so he's doing a PhD, so I'm pushing him with a PhD and some engineering aspects. So this is the main context. So Nawel is working very hard to get this thing to work, right? Just so you get a feel what this does. So this is the interpreter version of the addition primitive. So when you add two numbers, this is what it looks like in the VM. So we take the things that are on the stack, we check if they are integers. If they're integers, we add them up, and we check if there's an overflow. If there's an overflow, we fail. Yeah, we fail if there is an overflow, or we fail if some of the types are not the ones that we expect. If everything is okay, we push the result to the stack. Yeah, and what Druid is doing, it's taking that thing and other stuff from the VM, and it's generating automatically the compiler front-end code that is going to be executed at runtime to JIT compiled code that will be executed later at runtime. So it's kind of a staging issue here. But so he's taking that code, and we have a compiler that takes that code and generates this code. We don't need to get too much into the details of this. So a couple of months ago, we said, okay, now we have a version that can JIT compile a lot of stuff. Yes, so Faro, just for so you know, right now can JIT compile out of the 200. So we have 225 bytecode that are defined, and the JIT compiler that we have in production can compile all of them, and it can compile a lot of primitives, so 130. Yes, so there are primitives that are defined both in the JIT compiler and in the interpreter. And Druid at this point, I don't remember when, it could compile 10 primitives. It could compile more maybe, but we tried the version with 10 primitives. Yes, so Faro, the JIT compiler in Faro in production, it was able to compile 70% of whatever we had in the interpreter. And what we generated, it was able to compile 46%. So you say, okay, yes, maybe with this, we can see already a speed up. I don't know. So yes, but there's a difference there. So what can these 10 primitives versus 130 do, right? And good things, okay, at least we had something that was working. We could run tests and they were green, so okay. And this was generating more than 10,000 lines of code, right? So it was a lot of effort. And we said, yes, we want to run the benchmarks. Let's run some benchmarks. And we had this thing, yes? So so here what we see is we have some of the really well-known benchmarks like regex DNA, nucleotide, Chaminios, I don't know. And we also run tests as benchmarks to see, okay, maybe if the tests run faster, we are going to see that. And what we see here is 3 box plots per plot. In blue, so on the left, we have the production VM. So we call it the stock VM, the one that you download from the internet. Then we have the interpreter in the second box. And the third one is Druid, the thing that we auto-generate. Yes? And we would expect that what we generated, since we are having a JIT compiler support, is going to be, it should be faster than the interpreter, right? At least, because we put a lot of effort on that. And you see now, actually, if you see this, what happens is that you see some of the benchmarks were kind of a la par with the interpreter. We said, okay, maybe there's something that we're missing. There were only one here in this slide that it was slightly faster, okay? This goes in the right direction. And we had some that were really slow. So we had a problem here, right? The question is, okay, how do we do to fix this problem? How do we get the information that we need to be able to fix this thing? We were thinking about profilers, yeah? And so either we develop a custom tool and it takes us 6 months to have a really well-done tool to profile this thing and get information, or we can try to use something that is out there. So I tried instruments, yeah? So do you know instruments somehow? Okay, a couple. So instruments is the profiler that comes with macOS. And you run an application and then it gives you just the call stack and the percentages where the time is spent in each function. Now, when you're debugging the VM and profiling the VM, you will see that this is kind of useless as a profile because all the information is kind of mixed. So we have a lot of things here. So all this is JIT code, so JIT compile code, and then understanding where the time is actually going, it's actually dispersed in many places. So now I wanted to take this a step further and say, okay, this is a good first step. I want to take this information and make it something useful with this. And fortunately, there is a way to export this data to an XML, right? Because it was not very straightforward. Actually, I had to update my macOS to the latest macOS, so this works. So only the latest versions can export this into XML, and when I have data, I can actually manipulate the data, and I can do whatever I want. And this XML has the shape of samples. So every time that this profiler that I ran was working on samples, so it was a time-based profiler, and it was running from periodically, and every time it ran, it was taking the stack trace and saying, okay, this time, this is your stack trace at this moment, and this is your stack trace at this other moment. And we have these samples with these stack traces, right? So this is XML, so there are a lot of messy details with the XML format that they have. I will not go into that. But I wanted to get into that and extract information from there. And if you see this stack trace, we can see stuff that is probably interesting. So the stack on the top, we see that it's a primitive that is being called from machine code. So, and the stuff from the bottom, we see that we're inside the interpreter and doing something, right? So one thing that we can do, so once we have this observation, is that, okay, maybe I can write a tool that can, based on these samples, somehow group them together and say, okay, all these samples are based on our garbage collection stuff. I don't care if they are in this function of the garbage collector. So this is garbage collection. And this is JIT compiler. This is JIT compilation. Here I am in the interpreter. I don't know. Yeah. So once I can get this to work, so this was just parsing the XML and dealing with the messy details of instruments, we can get something like this. So, okay, now I can know, given some benchmark, okay, I spent 20% of time in interpreter, 50% of time in this thing, and 10% on the other, right? So, okay, how can we use this now? One of the things that we did is, so at some point we started with this case that we had with Nahuel. We took one of the benchmarks. Actually, we see two benchmarks. So we are running the tests of the kernel, the Faro kernel, and we're running the test of the Opal compiler. And we run this to compare, okay, how different it is, the profile from the JIT compiler we are generating and the JIT compiler that is there on production. Yes, so are they behaving differently? Yes, and here we see several things. So here the color, so the blue ones is machine code. So I will explain this to you because I wrote it. It's not it's just for me, these names. So the red ones are samples that I see that there is a transition between machine code and the runtime, but I didn't want to go into details in there. So those are trampolines. Those are just transitions, and there are a lot of different transitions there. I didn't want to go in details there. We see that sometimes we have primitives that are being called by machine code. We have primitives in light blue there that are being called by the interpreter, yeah, because we have different versions of the primitives and different ways, different paths to arrive to the same place. We have in green JIT compilation, so time spent JIT compiling code, so not executing the JIT compiled code, but just compiling the code. The interpreter in red, no, in orange, so it's these big things here, right? And others, so whatever I didn't want to put effort in grouping, right? So now we can see here that there is a big difference to the left. So the left bar and the right bar, they are really different, and both of them actually have the same profile. So we have a really big problem. And I would say here, so these are relative, of course. I'm not taking the absolute time. I'm just showing a percentage over the total time. And here we see that the left bar is always taking more time compiling code than the right the right bar, right? So, okay, that's a good start. If I look at this, I can just say, okay, we are missing something in the compilation. It's very easy to see this. So with this, actually, and then just a couple of minutes of putting the right breakpoints in the right place, we arrived to this. So, and this was super funny. So that's part of the story. So I want to tell you. So what happens actually? So we're not translating all the bytecodes nor all the primitives. So there are 1 or 2 bytecodes that we are not translating. The one that we decided not to translate, it was this context. Yeah, when you are verifying the context, because we said, okay, that is used in the slow path. That is usually you will use this context when you want to debug, when you have an exception. So we don't JIT compile that. It shouldn't have it shouldn't be a really big deal. So we didn't implement that one. But Cogit, the JIT compiler we have, is an all or nothing compiler. So when it looks at the method, it will say, okay, can I compile all the bytecodes here? And if I can compile all the bytecodes, it will compile the method and it will generate machine code. And otherwise, if there is at least one bytecode that is not supported, it will say, no, sorry. And of course, it doesn't do any detection of dead code. And what I found is that, look at this method. This is the value method in block closures. Yeah, so, and what you see, so, okay, it's calling a primitive, and then we have the fallback code that gets compiled with the method. And then here we have, okay, false if true, if false. So, okay, dead code, but this is a glorified comment. So this is a comment that has syntax highlighting. We can see it like that. But actually, this guy is really it was trying to reconstruct the context as it was done before. I don't know, many ages ago. And of course, it's using this context here and here. Of course, what this means is that value colon will never get JIT compiled. And we use that in loops every time. So every time that we enter in a loop, we are going over the slow path. And we are trying to JIT compile this method. And this method cannot be JIT compiled. So the next time we are going, in the next iteration of the loop, we're going to try again to JIT compile this guy. and so on. So we just remove that part. And Faro doesn't have that anymore. Now, this idea of comparing profiles is also nice, for example, if you want to track some performance issue over the history of your project. So, for example, here what I did is I took the history of the VM. We had some pointer regression. You can see it, and you can see when we fixed it, right? We can go in details on where, why the regression was. So we changed a bit in some refactoring the heuristics, deciding when a method was going to be JIT compiled. So we broke it and then we fixed it. But if you don't have this, it's very difficult to spot something and to understand, oh, I messed up. So, and this is a really simple tool that we did in one afternoon, and it can be really useful. So now, some more analysis that we can do this. So we can also, so I showed you the relative numbers in percentages. We can do the absolute version. And here, for example, if I compare the profiles of this test that I was showing you before, here I put the interpreter too. So the interpreter, okay, you can see the interpreter spends too much time in the interpreter, which is okay. But here you can see some differences. So if we plot these two as relative ones, they look really similar, but still, so the percentages will be really similar. So you will not spot the issue. But when you plot them with absolute values, you can actually spot things like, okay, we have a bit worse quality machine code somewhere, because we spend more time in machine code, but still, so the same program spends more time in machine code and it's slower. So there's something that is not right there. And the other thing that we can see is that we spend more time in primitives, yes? And we can use this same idea of going into the samples and trying to just look at the profile that I got and to do some VM profiling, doing a drill down on the samples that are of interest to us. So for example, let's say I want to take a look at the primitives, yes, because I spend time in primitives. Okay, how can I get that? And here, for example, we can, if we ignore the samples that are not primitives, so we just take the samples that are primitive samples, and then we can extract the primitive name from the trace, and we can do stuff like this. So I can now say, okay, look, this guy called this primitive so many times, and so on. It spent so much time in those primitives. And so here what you see is here you see the list of all primitives that we had in the profile. We have the default, the production VM, the one that we generate, the new one. And here it's a diff. Actually, what we do is I take the blue from here and the blue from here, and here I have the difference between the two blues, and I have the difference between the two reds and the difference. So here I can see where is the actual thing that we need to improve. And so here these are the two different benchmarks. For example, the kernel, of course, the kernel test will do something different than the Opal tests. So they don't exercise the same kind of stuff. But we can have here, we can see some low-hanging fruit. So, look, the primitive add and the primitive output probably deserve some love, right? Of course, then after some bit of well-placed work, because once you have the profile, spotting the issue and fixing it is pretty easy. It's better than doing it in the dark. We got better. So now, so these are the benchmarks that Noel ran, what, 1 month ago, 2 months ago, for one paper that we wrote. So now our new JIT compiler is 2 times faster than the interpreter on average. We're still 70% from the production one. Yes, there's some stuff that we are not supporting. We are getting there. So that's why when Steph says, oh, okay, Druid is there, I would like to have at least to be 90% of the one that is on production. And that should be doable. So, for example, some things that we are missing, actually, we have implemented them in the last couple of weeks. So we have static type predictions, some people optimizations on conditionals that are there in production, in the production one, but we didn't have it in our compiler generation. So this is nice. So what's next? So of course we are going to continue improving the compiler and getting more performance and squeezing that. Now there is a guy, Mateo. Are you there? Mateo is there, yes. So Mateo is a very smart student. He's working on extending this to have perf support. Do you know what perf is? Some of you? Okay, so perf is kind of the equivalent of instruments, but for Linux. So it's the profiler that comes and it has a lot of things. And turns out that getting information that we can work with out of perf is not so easy. So Mateo is working a lot on parsing the output and getting the right parameters on perf so we can replicate the same thing on Linux. And one of the things that I want to do in the short term, because if we care about performance, we need to do performance first, as you do with, if you want that your application works correctly, you go and do tests, because you care about that. Okay, if you want to care about performance, then we need to think about that. And we need to have it really in our life cycle of development. So we need to track Faro's performance every day, every week, every month. So for example, so one of the things that Mateo is probably going to explore before the end of his internship is to work on some dashboards to understand, okay, performance. Did I mess up? I want this information that I just showed you here, that is online and available every day, every build. Yes. There's a lot of work to do that because benchmarks, they take a lot of time to run to have good results and so on. But we're going to do something around there soon. I have a project also on benchmark generation, so we are really lacking work on having good benchmarks. So we are using the ones that were there available in the community. We are running tests for benchmarking, but okay, I don't know, if Rosal is slow, I don't have a benchmark that tells me why, or I don't know. So we need somehow benchmark programs that measure the performance of the thing that we care about. So if you have some idea, something that is important for you that we can use as benchmarks and example programs, so come talk to me. I want to build stuff that will get us better. So some takeaways before finishing. I'm 22 minutes, so I'm okay, right? Good. So we can use simple custom tools to do complex stuff. So I think that we all know that, but okay, here it's just a story of one particular one with a VM. So we do test first for good behavior. We should go bench first for good performance too. So thank you very much. Yes.
One thing I didn't understand, you said you reached 70% of the stock VM. So
yes.
Was it is it 70% the execution time or the speed? So is it slower or faster than
the one that we are generating is still a bit slower.
Oh, okay.
Yes, we are getting there, but. Okay, so thank you very much.